So in this video, I'm going to very briefly talk about the indeterminate form infinity minus infinity. Now notice the kind of really important thing in this situation is that one of them has to be positive and the other one has to be negative. That's going to be really important as I go through and do these particular problems. So the most important thing to know about this one is, again, that L'Hopital's rule does require the use of fractions at some point in some way. So what I'm going to have to do is I'm going to have to turn these two functions, f of x minus g of x, into some kind of a quotient somehow, some way. And I'll say, just from personal experience, most of the time it's fairly obvious because a lot of these problems do involve trigonometric functions. However, it's not always particularly obvious, so I'll kind of point out some things to do in those situations. So I'm going to just go ahead and jump right into my first example, which is the limit as x approaches pi over 2 from the left of secant x minus tangent x. And so again, I just always want to verify that this is the correct indeterminate form. And so I want you all to think very briefly about what secant looks like from this perspective as it heads toward pi over 2. Well, secant, again, is 1 over cosine of x, and cosine is positive in the first quadrant, but it does head towards 0 as pi over 2 approaches it from the left. So what's happening here is this has ended up heading toward positive infinity. And then we are subtracting this by tangent of x, which is also sine x over cosine x. And again, cosine and sine are both positive in that first section of from 0 to pi over 2 from the left. And so again, this is also going to head toward positive infinity. So we've got positive infinity minus positive infinity, and that's, of course, our indeterminate form. We got one that's positive, and then this is going to become negative here. But again, I mentioned before, I want to make this into a quotient, and for the most part, it's fairly obvious. I'm just going to use these trigonometric identities, the reciprocal identity and this ratio identity, to turn it into fractions. And so that's what I'm going to do is I'm going to just go ahead and approach it from this perspective. I'm going to write it as the limit as x approaches pi over 2 from the left of 1 over cosine x minus sine x over cosine x. These two things already have a common denominator, so I can just merge the two fractions and say that it is 1 minus sine x over cosine x. And just to prove my point that this is still, in fact, a indeterminate form, if I plug in pi over 2 here, this is 1, so we have 1 minus 1, which is 0, divided by cosine of pi over 2, which is also 0. So this is still an indeterminate form. And now I can apply L'Hopital's rule, which is take the derivative of the numerator. So let me write that down. Limit as x approaches pi over 2 from the left. The derivative of 1 is just 0. The derivative of sine is cosine, and we are subtracting them. And then in the denominator, the derivative of cosine is negative sine. So 0 minus cosine is going to give me a negative cosine, so these will end up being both positive. The negatives will cancel out. So where I'm at this moment is I've got the limit as x approaches pi over 2 from the left of cosine x over sine x. You could also write that as tangent if you really wanted to. But essentially, at this point, I'm ready to just plug this in and see what happens. Cosine at pi over 2 is 0, and sine at pi over 2 is 1, so my final answer here is just 0. Okay? So, again, the big thing here was just to remember our trigonometric identities and to make the switch. And the same is going to happen on the next one. So, we still have another situation where it involves a trig function. The limit as x goes to 0 of cotangent x minus 1 over x. Now, I do again want to verify that at 0, these are going to be, the appropriate infinities. Now, I think this one's a very interesting function or a very interesting limit in general because, and I think this is kind of interesting, if you look at limit as x approaches 0 from the left, what cotangent does is it goes toward negative infinity minus 1 over x turns into negative infinity as well. So we end up having one that's negative and one that's positive. However, if I switch it and I do the other side, the limit as x approaches 0 from the right, cotangent heads toward positive infinity, but so does 1 over x. So now we have one that's positive and one that's negative. So I think that's kind of interesting about this problem, again, is they switch. Depending on whether you're on the left side or on the right side, they switch signs, but it's still infinity and infinity that are opposites of each other. So let's go ahead and, again, try to apply L'Hopital's rule to this. And what I want to write is I want to write this, cotangent x divided by, or excuse me, cotangent x minus 1 over x as a quotient, as a fraction. So let's write cotangent x using our trig identity. It's going to be cosine x over sine x. I will have to make a common denominator in this situation. So let's see. That cosine is going to need an x, so we'll write it as x cosine x. That 1 is going to need a sine x, and I'm going to write that as x sine x in my denominator. So I'm going to apply L'Hopital's rule, which is going to involve taking the derivative. Now, I am going to have to use the product rule on these x cosines and x sines. So let's go ahead and do the first one. If I take the derivative of just the x, we're going to have 1 times sine of x. And if I take the derivative of just the sine, we're going to have x times cosine x. So I'm going to kind of follow the same process. I'm going to work on just subtraction first. So minus cosine x up here, because the derivative of sine is cosine, and product rule with this 1 times cosine x, or x times cosine x. So if I take the derivative of the x, we get 1 times cosine x. If I take the derivative of cosine, we're going to get a negative sine of x, and then we're still at x at the beginning. Now at this moment, I'm going to try to combine like terms to simplify things a little bit. So this cosine minus cosine will cancel. And so we're going to be at limit as x approaches 0 of negative x sine x over sine x plus x cosine x. At this moment, I do want to verify, if I plug in 0, what's going to happen? Well, sine of 0 is going to be 0, so that's still a 0 in the numerator. Sine of 0 again is 0, and then I'm going to do cosine of 0, which is 1, but then that's times 0. So I'm still in a situation where that's an indeterminate form, so I'm probably going to do L'Hopital's rule again and see what happens. Again, this is going to involve some product rule. So let me go ahead and we'll deal with this sine of x first. The derivative of sine of x is cosine of x, so we'll write that down. We can do cosine of x times x next. So let's see. We'll take the derivative of the x and get 1 times cosine of x. And then I'll take the derivative of cosine, which gives me a negative sine of x times x. And then, again, product rule up here on the top as well. So the derivative of negative x is going to be negative 1 times sine x. And then the derivative of sine x is going to be cosine x, and that still had a negative x attached to it. Try to combine like terms. Cosine and cosine is going to make 2 of them. So I have the limit as x approaches 0 of negative sine x minus x cosine x over 2 cosine x minus x sine x. And again, I want to verify, just plug in 0 and see what happens. Well, that's going to give me negative 0, because sine of 0 is 0, minus 0 times cosine of 0, which is 1, so the numerator is going to be 0 at this point. 2 times 1 minus 0 times 0, because sine of 0 is 0. Well, so I have 0 in the numerator, but in the denominator, 2 times 1 makes 2. So I'm ready at this point to conclude that this original limit, all the way up here at the top, cotangent x minus 1 over x, is actually just 0. Now that I've got that handled, we'll go ahead and flip over to our final example. And this one is going to be a little less obvious. So this one says the limit as x approaches infinity of x minus ln of x. So again, just verify very briefly that this is in fact the appropriate indeterminate form. As x goes to infinity, that goes to positive infinity. And for the natural log of x, as x goes to infinity, that's also headed toward positive infinity. So we are, in fact, subtracting positive infinity minus positive infinity. So this is the exact indeterminate form that we're looking for. But again, this one is not going to be as obvious on how to write it as a quotient. So the trick to this particular problem is that I've got a subtraction of a natural logarithm. And so what I'm, in fact, going to do to make my life the easiest on this one is I'm going to rewrite x as a natural logarithm. And so the way I'm going to do that is I'm going to rewrite it as the natural log of e to the x. So here's the thing. If you take the natural log of e to the exponent, they essentially cancel each other out. They're inverse operations of each other, and so you would just be left over with that x in the end anyways. But this is actually going to help me write it as a quotient, because if you subtract two logarithms, it's the same thing as dividing their arguments. So what I'm going to do is I'm going to rewrite this as the limit as x approaches infinity of the natural log of e to the x divided by x. And there is my quotient. There's my fraction. Now, one of the things that we should know, hopefully at this point, is that what we've done is we've composed, this is the argument, e to the x divided by x. Well, the natural log is just a function. So if I wanted to, I could actually take the natural log of the limit as x approaches positive infinity of e to the x over x. And once I figure out what this limit is, I can then plug in the natural log and get the answer. So that's what I want to do at this point, is kind of focus on what's on the inside of these parentheses, that e to the x over x. And I can do L'Hopital's rule of that. So let me write limit as x approaches positive infinity. And if I take the derivative of e to the x, we still get e to the x. The derivative of x is just 1. And so I'm here that we've got the natural log of e to the x over 1 as x goes to infinity. Well, if I plug this in, e to the infinity is going to go to infinity divided by 1. Well, that's infinity. So I'm really just worried about what happens as the natural log goes to infinity. Well, it goes to positive infinity. And so that's actually going to be my final answer here, is that this subtraction, x minus the natural log of x, still goes to infinity. Okay? Hopefully this helps. If you have any questions, let me know.